Good evening. Tonight we're going to be thinking about what happens when a massive bolide of space rock hurtles towards planet Earth. This has happened at many epochs in, and especially before, human history. For example, there was an impact in 1908. This was when a 60-metre asteroid, the size of about 5 London buses, impacted in Siberia. This is known as the Tunguska event. It was a Tuesday morning of the 30th of June 1908, when over eastern Siberia there was a bright blue light, nearly as bright as the sun, that appeared in the sky. There was an airburst and then a shockwave, as though a stony meteorite had exploded. The impact event within Earth's atmosphere was believed to be at an altitude of 5 to 10 kilometers. When this reached the surface of the Earth, seismic activity measured to be magnitude 5 on the Richter scale was witnessed. This was a big deal. Fortunately, it was a very underpopulated area. Only 3 human deaths were reported, but there was widespread damage all across the forest. Over 2,000 square kilometres of forest were completely flattened, apart from a few stalks and strong tree trunks. Just to help you calibrate, 2,000 square kilometres is larger than London. Fortunately, that particular 60-metre asteroid landed in the forest. It did not land in a human-populated area. Let's fast forward in time to last Saturday. Last Saturday, an even larger asteroid flew past, larger than the 60 metres of the Tunguska event asteroid. And that asteroid, last Saturday, came closer to Earth than the gap between the Moon and Earth, captured in this iconic photograph known as Earthrise by Bill Anders on board Apollo 8, the first crewed mission to orbit the Moon. This iconic picture was taken on Christmas Eve in 1968. And I want you to think about the gap between the Moon, which is unusually for us in the foreground, and planet Earth. This large asteroid that whizzed by planet Earth last Saturday nipped between that gap. So I want to show you that asteroid this evening. We had a remarkable flypast. But before we get into that, let's just consider what is an asteroid. An asteroid, the name asteroid comes from the Greek word meaning star-like. But it's important to be clear, it is not a star. It is not in any shape or form a star. It's not radiant. It's a lump of rock. It doesn't give off light. So it has loads of mass, and it's a funny shape. It has its own little craters if it's been pitted by other meteoroids and any dust debris that it's encountered as it's been orbiting within the solar system. This one here, 951 Gaspra, was the first ever asteroid to be photographed. It was photographed by the Galileo mission in the early 90s. So the craters, the little craters that we can see on this asteroid, are a strong reminder that in space, things hit other things. And we can see that very clearly when we look closely at the Moon. The Moon is littered with craters. The Moon has no atmosphere at all to protect its surface from the impact of craters. And so we see very many of them when we observe them with a telescope, for example. So it's unsurprising if our nearest neighbour, the Moon, gets so many impacts, which are made manifest because there's no atmosphere to burn up the little examples that rock up. Sorry for that pun, by the way. It should be no surprise that some do come close to Earth. But when they get as close as half the gap between the Earth and the Moon, it is perhaps time to sit up. So I want to show you, first of all, what is the orbit of this thing that came so close last Saturday. What is the orbit of the asteroid known as NEO, that's Near-Earth Object, 2023, that's this year, the year of its discovery, DZ2. Whereabouts does it belong in the family of orbits within the solar system? We're very familiar with the array of planets and little dwarf planet Pluto just appearing there on the right. This is the solar system as we're familiar with it. But as we'll see later this evening, there's a lot more in the solar system in terms of numbers of bodies than are accounted for on this slide. But the orbit of this particular asteroid is shown here in white. So the outermost orbit here is that of Jupiter. The deeper orange orbit closer in is that of Mars. And the majority of asteroids in the solar system are in between Mars and Jupiter. There's a big asteroid belt there, as we'll see later. But as you can see, the white path indicated here represents the orbit of the asteroid that we're talking about. You can see it's quite an elliptical orbit, but nonetheless the Sun is at a focus of that ellipse. So it's part of the solar system, it's orbiting the Sun, but its path can impinge on the orbital path of Earth. It didn't last Saturday. Why do we know that? It's Wednesday, we're still here. How close did we get is quite an important question to ask. Well, it was this half lunar distance. Could it come closer in the future? Well, yes, it might. It really could. So the orbital period of this asteroid is 3 years, 1,098 days, 3 Earth years. So next time it comes round, it's had a little nudge or a little knock en route. Sure, it could hit Earth, or it could hit the Moon, or it could be completely knocked off course. But why was it, if it's got this periodic orbit of every 3 years, every 1,098 days, orbiting on its elliptical path around the Sun, why was it only recently discovered? And when was it discovered? It was discovered on the 27th of February this year. Why was it only discovered so recently? Well, it's worth commenting at this point that the discovery of near-Earth objects is hard. It's hard because, as I mentioned earlier, we're talking about moving rocks. We're not talking about radiant stars. So they're relatively faint. These asteroids, are often only visible for a few days or a week or two, depending on where they are in their orbit. If they are the far side of the Sun, we're not going to see them, because if they're the far side of the Sun with respect to Earth, then they're a daytime object, and you can't do optical astronomy during the daytime. It's strictly a nighttime activity. If you are talking about an asteroid on an elliptical orbit, then the syncing, the phasing of its elliptical orbit with Earth's fairly circular orbit is going to track with time. And until you understand what the answer is, you may not spot the pattern. So it's definitely hard. So detecting near-Earth objects is not easy. However, a wonderful project called EuroNear was specifically designed to find near-Earth objects. This is an international consortium initiated by Ovidiu Vadivescu and Mirel Birlan from Romania. This is the discovery image of the asteroid that we're talking about. It's that faint, innocent-looking blob in the very centre of the image with the arrows pointing at it. Now, let's just explain what these diagonal streaks are going across. Those are stars, and normally, of course, stars with a well-tuned telescope, stars appear as pinpoints, and the telescope will track them through the night sky. Their movement, of course, caused by the spin of the Earth. But if you set your telescope to have non-sidereal tracking rates, so it isn't following the stars, but it's following whatever it is you're interested in, then whatever it is you're interested in, if you've got the tracking rates right, will appear like a point source, and everything moving through the sky at a different rate will just appear as a streak. So that's what's happening here. And here are all the people involved in making that discovery. Some of the people here are software engineers. I believe it was Costin Baldir who made the actual discovery. But amateurs contributed to the determination of the orbit that confirmed it was heading our way. I'm using our inclusively here to mean the Earth and the Moon. So a lot of people are involved in making these necessarily multi-epoch observations in order to determine, is the orbit of this particular asteroid potentially a threat, or are we completely safe? When I heard that this asteroid was going past last Saturday, I decided I should observe it. And so I used some of my global jet watch observatories, the one that were facing the right way and the ones that didn't have cloud cover. And on Saturday, that translated to South Africa and to India. This is a picture of the India observatory, and this is a picture of the South Africa observatory. So I used both of these telescopes simultaneously on Saturday late afternoon and Saturday evening UK time to see if I could observe this same asteroid from two different points on Earth. I was in Oxford, where it was bucketing it down with rain, and operating those two observatories over the internet. And when I said the observatories weren't covered in cloud, that was fairly true, but not completely true. This is a view through the finder scope of the South Africa telescope, and this gives you a sense of the clouds that I was facing on that evening while I was observing, and it was a pretty similar story in India. However, there were gaps in the clouds, and I have two hands, and I was able to track those telescopes through this rapidly moving asteroid. Moves like the clappers with respect to the sky background, and this is the... So I'm tracking with respect to the stars, and that diagonal line there is the movement of the asteroid going through that particular stellar field. This movie is speeded up by a factor of 20. Each exposure that I took was 20 seconds long, but I'm showing these here as stills for about 1 frame per second. So that was India, and this, at the same time, was South Africa. So there was actually a gap in the clouds at both observatories at the same time. Plenty of occasions where one was cloudy and one was not. But anyway, that was it. Oh, those, see that little appearance of a few things there? That's independent of the, it'll come round about now. There we go. Those are just cosmic rays. So they too are falling out of the sky, but not quite so much danger. But there was a lecture about 2 years ago on those, the title of which was Fast and Furious. Because they are, but they don't have the same kind of mass that asteroids have. So ultimately, I was able to end up with these two simultaneous time lapses of the passage of the asteroid last Saturday. These two are simultaneous observations. And you may be thinking to yourself, well, Earth isn't that big, and indeed, in the previous lecture, on Christopher Wren, we learned about how the parallax angles of stars won't change very, very much if they're reasonably far away, even if we sort of move the Earth from one side of its orbit around the Sun to the other. Well, that's true, but that's for stars which are much, much further away than the Moon, or anything which is half the distance to the Moon. So these stellar fields being different is another reminder of just how close this asteroid is that is imaged moving here. So just a reminder about the parallax. Christopher Wren and Robert Hooke built the monument to function as a zenith telescope. Here was Wren's design, in order to measure the distances to stars. The experiment didn't work. It was a very intelligent attempt, but they didn't know, of course, a priori, how distant the stars were. That was the point of the experiment. But the stars were so far away, it was not possible to measure any parallax angle for these particular stars. The geometric basis for what they were trying to do was completely sound, but what angle you measure as you measure from different locations with respect to your target depends on how distant they are away from you. The asteroid that appeared on Saturday was so close that even from the relatively close locations of India and South Africa, measured at the same time, so you're not moving which part of the Earth's orbit around the Sun you're taking the observations from. Those were simultaneous observations, and the separation of my India observatory and my South Africa observatory in latitude is about 45 degrees, and in longitude it's about 60 degrees. So they're not even an Earth's diameter apart. And yet, this is how far apart those two stellar fields actually were. So I'm just zooming in here to how far apart they actually were. So these grid lines are about 1 degree apart. And so that's how far apart on the sky, when viewed from over here in South Africa, the asteroid appeared to be, whereas over here in India, the asteroid appeared to have a completely different background of stars. And so it was fascinating to realise that this exact same body was so close that they had different backgrounds, even from two parts of Earth that aren't so far apart. Much bigger camera, and I could have got them on the same detector, but the size of the detectors on these telescopes is about half a degree square from top to bottom. So I mentioned earlier that this particular asteroid, NEO 2023 DZ2, was larger than the asteroid that caused the devastation in that Siberian forest in 1908. But exactly how large is it? I needed to look this up, and so I dialed it into the internet, and probably the most helpful answer came from the Metro. I mean, seriously, it gave me a really useful calibration. It said an asteroid about the size of the Big Ben clock tower, the Elizabeth Tower. And that's the kind of size that those of us who pass through London occasionally can relate to. It's possibly a slight overestimate, by the way. It's probably a bit nearer 70 metres. Orbital today, I think we're out by probably a factor of 2. It depends on how big you think a skyscraper is, but typically they're taken to be at least 150 metres. Probably the most surreal answer that I came across on the internet was in the Jerusalem Post. Astronomy is famous for using different units, but using the tuna fish as a unit of length is a new one on me. But it's 22 of them. And I must admit, I don't think I've ever seen 22 tuna fishes in the same place. But there you go, it's quite large, way larger than this lecture theatre. So, had it have hit Earth, it would have done a lot of damage. So let's now think about that kind of damage. What does happen when a large asteroid impacts on the Earth? A whole series of really bad things happens. First of all, there's a blast wave, a shock wave, because the asteroid is typically travelling at really fast speeds. The fast speed of that asteroid, through the images I was just showing you, was in excess of 10 degrees per hour. That translates to something like, I think it was 17,000 miles per hour, in excess of that. So really, really fast. Way faster than the speed of sound, so you get a shock wave. And that's a large shock wave because you're dealing with a large massive body whooshing through Earth's atmosphere. And so you get frictional heating. And so the atmosphere gets superheated. It gets heated very, very rapidly, and very, very hot things will set fire to whatever's in the vicinity, except ocean, of course. But that's not a great outcome either. We'll get to that. The kinetic energy of the large asteroid, so that's the energy that the asteroid has by virtue of its motion, by virtue of its speed and its mass, that gets converted into heat. Tremendous amounts of heat when the asteroid impacts on Earth. If the asteroid first impacts on the ocean, then that water will get instantaneously vaporized into steam, which isn't good for living things either. Whenever the asteroid ultimately hits hard ground, there will then be something of seismic activity. Any oceans anywhere nearby, massive tsunami, much, much faster than the one that did all that damage nearly 20 years ago. So there will be a tsunami for sure, many tsunamis probably. If the asteroid penetrates Earth's crust, then molten rock will spurt out at many kilometers per second. So these are like intercontinental ballistic missiles, directionless, just heading out to cause havoc. And when those spurts of molten rock or lava eventually return to Earth, they'll ignite fires. Forest fires, bushfires, cities, anything in their path will catch fire. So it's not a great outcome. It's been conjectured that a large asteroid is what killed off the dinosaurs. It's very widely accepted that the dinosaurs, which had been stomping all over planet Earth for a very, very long time, disappeared very, very suddenly. So I think it's widely accepted that there was an apocalyptic event which led to the end of the dinosaurs. I don't think it's completely conclusively determined that it was necessarily an asteroid, but a large asteroid fits many of the facts, sinking into the North Mexico coast. So obviously that if it was a large asteroid that did indeed wipe out the dinosaurs, we know that that was well before humankind existed, and there have been another set of examples of large asteroids that have impacted directly onto Earth's crust. So I thought I'd show you a few greatest hits. So what do we have here? This is the meteor crater in Arizona, known as the Baringa Crater, after Daniel Baringa. This is over 1 kilometre in diameter. Modelling suggests that it was formed about 50,000 years ago by the impact of a meteorite that was 50 metres in diameter. So that's slightly smaller than the Tunguska event, slightly smaller than the asteroid that did its flypast on Saturday. It's been modelled that it was moving at a relatively leisurely 12 metres per second. So that was thought to be a nickel-iron meteorite. It just so happens in our home we have one of these. It's a family heirloom. We don't have dinosaurs as our ancestors, by the way, but this particular meteorite was discovered by my great-grandfather-in-law in a little plot of land where he would grow crops for the family to live on in a little village in Warwickshire. So it's about the size of my fist. So it was probably a spectacular shooting star when it came through the Warwickshire sky, assuming it wasn't cloudy, assuming it was nighttime, because this is quite unusually large for a meteorite, certainly to be found in such pristine condition. There are some exciting examples of greatest hits in Africa. This one is in the Kalahari Desert in Morocveng, in the northwest province of South Africa, not too far from the border with Botswana. This is it without water, and this is it with water. So it's quite useful when it does fill up with water. It's thought that the asteroid or great big meteorite that gave rise to this was between 5 and 10 kilometres in diameter. In itself, this crater is about 160 kilometres. It's thought that this happened about 145 million years ago. But happily, it fills up with water these days. In May of 2006, a group of scientists drilling into the site announced the discovery of a 25 centimetre fragment of the original asteroid, so several times larger than the one we have at home, the size of my fist. It was about 770 metres below the surface, and there were other little fragments as well of the meteorite as it landed. So it seems like a very clear association: craters, meteorites, or asteroids, depending on the size. Things hitting into other things in the solar system, besides the moon, which we've already talked about, happen with other planets as well. In the mid-90s, comet Shoemaker-Levy, number 9, collided with Jupiter. So this was discovered by Caroline Shoemaker, Eugene Shoemaker, and David Levy. It was discovered in 1993. It went thwack into Jupiter into 1994. Before it went headfirst into Jupiter, this comet had an orbital period of about 200 years. It was determined by successive observations working out the trajectory of the comet with respect to the rest of the solar system. It actually broke apart during approach, but it caused a lot of excitement when it was discovered because it was the first comet discovered to be orbiting around a planet, admittedly a very massive planet, Jupiter, rather than orbiting around the Sun. So that was pretty exciting. Almost certainly Jupiter, which is really very, very massive relative to the other planets, captured this comet probably a few decades previously. So this is an image from NASA and ESA from the Hubble Space Telescope showing the different fragments as they went thwack, 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 thwack into Jupiter. Here's some other imaging from ESO. Loads of telescopes all over the world observed it break up and then go headfirst into Jupiter. So it's not just planet Earth that gets hit by asteroids and comets and meteorites. Other planets will have them as well, but clearly they have the potential to do a lot of damage here on Earth. The Verdeford crater is in the Free State of South Africa. The diameter of this one is 380 kilometres. It's conjectured that the diameter of the asteroid which gave rise to this was 25 kilometres. So this is the largest verified impact structure on Earth. The time of the impact was dated to be about 2 billion years ago, and the speed of this large asteroid has been modelled to be 25,000 metres per second. We're talking about enormous energies. So how many asteroids are out there, and how much risk are we at here on planet Earth? The short answer to how many asteroids there are in the asteroid belt between Mars and Jupiter is many. Have we found them all? No, we have not. Opinions differ as to how many asteroids we haven't found, because we haven't found them. It's an unknown unknown. But I have seen some remarkably precise percentages for something which isn't actually known. But I'm not going to quote those to you because I don't know how real they are. How many asteroids are out there? How many do we know about? Well, this graph here from NASA plots year of discovery on the horizontal axis and the cumulative number that have been discovered on the vertical axis. So blue is the all of the asteroids, including the little ones. The red ones are those that are bigger than a kilometre. So blue is less than a kilometre, but all the detritus really. So that's the most numerous number of asteroids. And then this orange colour is those that are larger than 140 metres. So as we might expect, there are numerous small asteroids, and there are few, but not vanishingly few, very large asteroids. So there are many more little ones than there are big ones, as we might expect. And that's also represented here on this plot, where it's a slightly busy plot, but let me just explain it. So on the top horizontal axis, we've got the diameter in metres. So 1 metre, 10 metres, 100 metres. It's a logarithmic scale. And if you make assumptions about the composition of the asteroids, then that gives you a mapping to kilograms on the second top, the highest top horizontal axis. Bolide energy, kilotons, TNT equivalent, large amounts of energy basically is plotted on the bottom axis. The closer you are to the right, the more energy. So unsurprisingly, the big ones, more energy when they go thwack. And then this is the cumulative number impacting Earth per year. So there are lots and lots of the little ones, and they just manifest themselves as things we never see because they burn up in the upper atmosphere, or pretty shooting stars, which are very nice to see, or occasionally ones like the one that we have at home that landed in that Warwickshire vegetable patch. But then you can see the probabilities here. Every century you'll see one that's 10 to the 7 kilograms in mass. This is an averaged type plot, but it quantifies how rare the larger asteroids are thought to be. But it's important to appreciate, A, they're not vanishingly rare, and B, we don't know everything that's out there anyway. The asteroid that did the close flypast on Saturday was only discovered on the 27th of February, about a month and 2 days. So this shows you the inner part of the solar system again, Sun and Earth and Mars and Jupiter, and then the asteroid belt, which is, as I mentioned earlier, in between Mars and Jupiter. There are different types of asteroids that are represented here. The so-called typical asteroids belong in the main belt. But we also have the so-called Amor asteroids, which are the ones in this sort of white elliptical orbit here, so larger than the orbit of the Earth and potentially Mars as well. So Amor asteroids don't cross the orbital path of Earth, but they may cross the orbital path of Mars. And indeed, a new crater appeared on Mars on Christmas Eve of 2021. That was not there before. It suddenly appeared, and it was accompanied by a magnitude 4 Marsquake, which is Martian for earthquake. So those are the Amor asteroids. But the Apollo asteroids, of which DZ2, which I showed you earlier, the one that did the flypast on Saturday, is an example of the Apollo asteroids. And the Apollo asteroids is the collective name given to a particular type of near-Earth asteroid. It's the sort where the orbital semi-major axis, so the radius if it were a circular orbit, but most of them are elliptical because they keep, or occasionally from time to time, knock into other things in the asteroid belt. This parameter of the orbit is larger than the Earth-Sun separation, which is known as 1 astronomical unit, but the perihelion distance, which is the closest approach between the asteroid and the Sun, Helios, that periastron distance is less than the Earth-Sun separation of 1 astronomical unit, 1 AU. So those are the asteroids we really want to watch because they might well cross Earth's orbit. Had the angle of DZ2 been a little bit different from what it was, it would have gone thwack onto Earth, and we would have been having a different conversation, potentially, today, if we were still here to have had the conversation, of course. How many Apollo asteroids are there? Well, 17,540 are known so far. 12% of these are identified as potentially hazardous asteroids, potentially hazardous objects, PHOs in the jargon. JPL has a register, a threat register, a risk register, if you like, of all these things. And it makes for some quite interesting reading, but I don't recommend it as bedtime reading. So if you have interactions within the asteroid belt or from other asteroids further out, the Trojans, for example, if there's an interaction with the gravity due to Jupiter, their orbits will change. They will move along a different path. So we have to keep watching. We have to keep vigilant if we're to spot these massive bolids of space rock coming towards us. So how do you identify an approaching asteroid? Well, this can be answered at a number of levels, but I just want to tell you what happened when my friend and colleague, the instrument scientist on the Global Jet Watch, Stephen Lee, started observing DZ2 from his garden in Australia. It was about the only bit of Australia that didn't have clouds on Saturday, as far as I can tell. And I joined him over Zoom. This was a few hours before it was dark in India and several hours before it was dark in South Africa. And I joined him over Zoom, and as we looked at these images coming in from his telescope on his computer, the conversation went something like, which one is the asteroid? There seem to be a lot of streaks in this image. Well, of course, we know, and we soon clocked, that it was this little one here. What are these other long streaks that we're seeing? Well, those are satellites moving on their orbits around Earth, but reflecting just enough light that they appear as streaks because they're moving faster than the stars are moving. So they generally muddle up the picture slightly. Here, it was pretty simple to discern what was going on after a moment's thought. But if you had a lot more satellites, you'd make it a lot more difficult. I'm going to return to this point in a few moments. But first, I want to show you an image of Sir Francis Graham-Smith, who was the 13th Astronomer Royal. And he wrote in 1982 the following warning: the cumulative effect of an ever-increasing number of long-lived satellites represents a very serious hazard to optical observations. That warning was written 4 decades ago, when the number of satellites that were up was vastly smaller. So what do we mean by a serious hazard to optical observations? We probably mean that the images we take have streaks, much like the last few that I showed you. But I put it to you, it's going to get a whole lot worse than that. And let me show you why I'm concerned about this. So can we see what's out there? Can we see what's coming towards us? Can we see the threat? So this shows you the plot with the year on the horizontal axis and the cumulative number of satellites on the vertical axis. This plot and all the data were gathered by my friend and colleague at Harvard, Jonathan McDowell. And he has a great website, planet4589.org, that you might like to look at. Back in 1982, when Francis Graham Smith issued that warning, there were about 350 satellites that were orbiting around Earth. Now it's above 7,000. So the numbers have increased considerably, but they're going to get bigger. Just at the end of January in this year, getting on for 4,000 SpaceX Starlink satellites and over 500 OneWeb satellites have been launched. So what difference does this make when you're taking an astronomical image? This is a nice astronomical image. It's from one of the commensal cameras from one of the Global Jet Watch telescopes. Lots and lots of stars to give us onboard photometric data to go together with our spectroscopy data. Fantastic for science, unless these guys rock up. These are Starlink satellites whooshing through our field. And here's a zoom in close to the target that we were observing at the time. So starlight streaks across astronomical images are increasingly a thing. These, on this table here, this is listing the expected number of satellites in the next few years. So the total number is going to increase by a couple of orders of magnitude. It's going to make it very difficult to do optical astronomy without light contamination streaking through the sky, moving illuminated graffiti through the sky. Jonathan has plotted the distribution, the expected distribution of, I think this is just the Starlink satellites. Now, I don't know if you can make out underneath these blue points the shape of the landmass on planet Earth underneath. If you can't, maybe that's sort of the point. There are going to be a lot of satellites up there. Now, of course, on this plot, the size of the dots does not scale with the size of the satellite, but they're moving. They're going to be streaking through our images. So if you think that Romanian-led team, EuroNear, did really rather well spotting an asteroid just a month ago and warning everyone on Earth, and then it was determined that no, it's not going to hit Earth, we're good. If you think they did really rather well getting all that data in a month when it's winter in the northern hemisphere and there are loads of clouds, you're right, they did really well. But once you start littering the sky with this moving graffiti, it's going to get a lot harder to make the necessary observations to find more asteroids, specifically the ones that might pose a threat to Earth. And we do live on a dangerous planet. In my first lecture at the start of this year's series on cosmic conclusions, I spoke about the end of planetary atmospheres. And I spoke then about how the tiniest concentration, relatively tiny, about 400 parts per million, of heteronuclear molecules, such as CO2, such as methane, can seriously lead to a damaging positive feedback effect in our atmosphere when it's a concentration of those heteronuclear molecules that is as slender as the number of caffeine molecules in a mug of coffee. And I discussed in that lecture, the end of planetary atmospheres, that we are in danger. We need to plan ahead and understand the threat, and we need to put our collective minds together internationally to overcome it. We need to do the same thing if we're going to survive asteroids impacting on Earth. How we as humans respond to the threats that do face us from outer space, from our own poor stewardship of this planet, will determine our survival or not. On a slightly lighter note, I really recommend the movie Don't Look Up. If you haven't seen it, it's great entertainment. It is political satire. Meryl Streep is an extreme right-wing US president. Meryl Streep is wonderful, of course, but the mind boggles. These two are scientists who are trying to make the case to politicians who don't want to hear, because they've just got their eye on the next election, the imminent danger that was faced by a much more dangerous asteroid in that film than we faced with GZ2 last weekend. Asteroid impact avoidance is a necessary industry, and it is a serious industry. If we can see through all the satellites and the clouds and find out rocky asteroids which are heading our way, we can do something about it. And this was exemplified spectacularly last September. I want to tell you now about the DART impact. This was not a dart in the sense that they're played with here on Earth. DART here stands for Double Asteroid Redirection Test. It was a proof of principle test to see if you throw something reasonably massive at an asteroid, can you alter its orbit? That was the test. So think of this like galactic snooker. In snooker, you fire the cue ball at something, and if you're really skilled, that something is one of the other balls, and hopefully the right colour goes in the right pocket, and all that sort of thing. It's a highly skilled game involving conservation of linear momentum, transfer of linear momentum from the cue ball to the other ball, sometimes spin, and all that kind of good stuff. So galactic snooker is how we might be able to solve asteroids that are heading our way. So on the 23rd of November 2021, a little satellite was launched, and this was a big experiment. This was doing something that had never been done before. Can you throw so much momentum at an asteroid that you can change its orbit? Impact took place on the 26th of September 2022. So the goal of the whole project was land on something that's either a minor planet or a moon, depending what you want to call it, in orbit around a little asteroid. So the little minor planet or moon is called Dimorphos, and it's orbiting around an asteroid. I'll show you a picture in a moment, an asteroid called Didymos. So the goal is you land the spacecraft on it with sufficient force that you change the orbital dynamics. Now, the reason for choosing a binary asteroid, an asteroid and a little moon, little mini planet kind of thingy, which actually is an eclipsing binary as observed from Earth, is that when you've got eclipsing binaries, you can readily measure the orbital parameters. So you know if when you hit it, you've made a difference or not. So it's an excellent choice of target. The success criterion was that there would be a change in the orbital period of Dimorphos, which was in excess of 73 seconds. So the normal orbital period was a shade under 12 hours, and they wanted to see if they could make the orbital period shorter by about a minute. So here's a schematic showing Didymos, the asteroid, and then Dimorphos, the slightly less massive little moon type thing. It's in orbit around Didymos. This is DART, the spacecraft, and this is the paparazzi, Lycia Cube, taking pictures. And of course, back on Earth, there were lots of images being taken. So this was operated by NASA and many other groups out of Johns Hopkins University. The actual orbital period, by the way, was 11 hours and 55 minutes prior to impact. following impact, that orbital period got shortened by 33 minutes, over half an hour. So the success criterion was 73 seconds, and they really overshot the success threshold. They achieved over half an hour change in orbital period in something whose orbit was less than half an Earth day. So fantastic success. The orbital parameters did change a little bit. Lots of good photography was obtained. I really recommend you go to the DART website to look at some of the fantastic footage as the DART spacecraft gets closer and closer and closer. Hold on to your chair while you watch it though. This is one of the observations showing the trail of dust and debris post-impact. So it's pretty clear that when you thwack a spacecraft into an asteroid, it does quite a bit of damage as well. It's not quite as bad as an asteroid hitting a planet, but nonetheless, you do break up the surface a bit, and that streak could be seen for quite a few days afterwards. So if we can detect asteroids coming towards us, the DART mission has demonstrated the proof of principle that clever engineers and clever orbital dynamicists can work together and can knock it off course. So that principle has been demonstrated. I think the difficult thing is finding the threats as they come towards us. So even though we have grounds for hope that we might be able to deflect an asteroid, and you don't need to destroy it to smithereens, you just need to knock it off course, much as you would in a game of snooker. But we still will need warning to plan exactly how to direct the spacecraft and with what momentum and what angle of attack we should give it. Advance warning to face these threats is critical. So not only do I think there are grounds for concern because of the satellites that are going to be rocking around up there in the coming years, I think potentially if we don't hold lots of ideas in our heads at the same time and face a great many problems that are facing humankind altogether, such as climate heating, we could risk solving one problem and leaving ourselves very vulnerable to the other problem. What am I talking about here? What am I getting at? I'm getting at some of the proposed solutions, or a small subset of the proposed solutions to avert catastrophic climate heating. I'm talking about a particular type of geoengineering where you modify the solar radiation by putting up lots and lots of aerosols, lots and lots of particulates. So the motivation for doing this is that you don't get as much solar radiation and solar energy landing on Earth and Earth's atmosphere and heating it up quite so much. Is that a good idea? Here's the problem. I mean, umbrellas are great, parasols are great. Shade is a really good thing. But if you do it in an uncontrolled way with the entirety of Earth's atmosphere, I think that's a real problem. If you inject particles into the stratosphere, those particles won't just absorb the solar radiation, or some of it, and hopefully reflect some of it back, but they'll also be reflecting it and scattering it in all directions, including back to Earth. So that particular kind of geothermal proposed solution, geoengineering proposed solution is fraught with danger. We will no longer have blue skies if that happens. We will have white skies, much like we get in the UK on cloudy days. This is a really dangerous idea, and it could go horribly wrong. We will lose the ability to see deeply into space. If you've ever tried observing when your neighbours have had a barbecue and there's smoke in the air, or there's lots of cloudy particles, or there's high cirrus, you don't get to detect very faint objects, and it's a disappointing astronomical evening. We need clear skies if we're going to be able to detect the threats that may face us. On that cautionary note, I will end this lecture, but I would like to say, keep looking up. Thank you.
Many, many thanks. We have time for probably 2 questions, so I'll start one from online. This one is, apart from the impact from an asteroid, what is the danger from a nearby supernova explosion or, for example, a gamma ray burst pointed towards the Earth?
Thank you. So, if we had, in our local neighbourhood, in the vicinity, the kind of progenitor star that could undergo a supernova explosion, then that would be pretty bad too. However, as I mentioned a couple of lectures ago, I spoke about the end of massive stars. There are no really massive stars sufficiently close to planet Earth that that's believed to be a real danger, we think. Gamma ray burst could be. Again, same sort of answer. Yes, in principle, yes, in theory, but we don't believe that in our context, planet Earth in the solar system, there's any progenitor of a gamma ray burst that's quite close enough to be a danger. So I wouldn't worry about those two too much.
How big could an asteroid get and the impact would still allow us to survive and the Earth to survive?
Oh, goodness. The answer to that would depend very much where the asteroid lands. If you go to a carefully, if the impact of the asteroid were to be in a carefully chosen bit of the Pacific Ocean, so nowhere near the Marshall Islands, nowhere near Hawaii, just a nice big deep bit, I should have thought, so any of the greatest hits that I showed earlier in my talk would result in tsunamis, and that would certainly cause significant loss of life on low-lying land. But humankind, I think, would survive. If you had one of those really big ones to land on the UK, for example, it's conceivable you could wipe out an entire nation. How big could it be? It certainly wouldn't need to be, I'm somewhat guessing here, but I think if you were getting on for several tens of kilometres, you would really want to be putting all your resources into deflecting that one rather than doing the calculation and wondering if you'd wipe everyone out. I think those are really rare, by the way, so don't lose sleep.
Do we have any questions in the room?
Thank you. As DZ2 comes so close to the Earth, is it likely to be affected by the gravitational field? And could we track a new orbit? Thank you.
I think we'll certainly be tracking DZ2 because it's of such great interest to us. I think it's unlikely that there would be a very dramatic kick or swing from planet Earth because we're nowhere near as massive as Jupiter, for example. Having said that, the trajectory so close to Earth was probably non-negligible, but my guess would be, without having done any calculations, you probably wouldn't see that play out for a few orbits, and indeed it might be completely impossible to pick out if there are other deflections and direct hits with other things on its orbital path. I think it's not likely that it will be too significant.
I'm afraid that's all the time we've got this evening. Professor Blundell's next lecture, which will round off the series, will be The End of the Universe, and that will take place on the 31st of May. We hope you can all join us then. Thank you very much, and thank you, Professor Blundell.